The universe feels softer around the edges, and even the oldest light in existence has enough patience to wait quietly for us to notice it. Tonight, we're traveling farther than almost any human journey has ever gone. Not with rockets or warp drives or dramatic countdowns shouted through loudspeakers, but with something much stranger and much calmer. We're going to travel with light itself. Ancient light. Light that began moving across the universe so long ago that Earth did not yet exist, the oceans did not exist, the sun did not exist. Not even the Milky Way looked anything like the galaxy we know today. Somewhere unimaginably far away sits a galaxy with the wonderfully complicated name Jades GS Z140, a name that sounds less like a cosmic wonder and more like a password you forget 5 seconds after creating it. And yet this tiny smudge of light may be the oldest galaxy humanity has ever seen, or at least the oldest one we've found so far. The truly astonishing part is not just its age, it's the fact that its light survived the entire history of the universe just to arrive here now. Landing delicately inside a telescope orbiting 1.5 million kilometers from Earth after 13.5 billion years of travel, after crossing expanding space, dodging clouds of gas, and surviving the violent evolution of the cosmos itself. Those photons finally reached us, which means that somewhere in the universe, a very ancient galaxy has been patiently sending us a message since before our planet was born. And tonight, we're going to sit quietly with that idea for a while. Before we begin though, I'd love to know something. Where in the world are you listening from tonight? Is it late evening, where you are? Early morning? Are you tucked into bed already, sitting near a window, travelling somewhere, or perhaps listening with one eye still open, while insisting to yourself that you're definitely not sleepy yet? And what time is it in your little corner of Earth right now? Funny, really. We're about to spend hours talking about distances so enormous that human history disappears into insignificance, and yet our lives still revolve around tiny glowing numbers on clocks. Midnight, 2 a.m., 11:47 p.m. The universe deals in billions of years, while we still get mildly stressed because the microwave says there's only 8 seconds left. If you find this journey relaxing or interesting, or simply a pleasant way to drift towards sleep, I'd be very grateful if you liked the video and subscribed. It helps this calm little corner of science reach more people who might need a quiet evening among the stars. Now then, let's settle in. You don't need to understand astrophysics tonight. You don't need equations or advanced mathematics or the ability to pronounce every galaxy name correctly on the first attempt. Frankly, astronomers barely manage that themselves sometimes. All you really need is curiosity. Because this story begins with something humans have always struggled to understand properly. Darkness. Real darkness. Not the kind you get during a power outage where your phone screen still lights up your face like a tiny artificial moon. Not the darkness of a countryside road or a cloudy night. Those places still exist inside a mature universe already crowded with stars and galaxies. The darkness we're talking about tonight came before almost everything. To understand why JD's GS Z40 matters so much, we first have to imagine the universe before galaxies properly existed. A time before spiral arms, before planets, before constellations, before anything familiar decorated the sky. And strangely enough, the story begins not with stars, but with silence. The early universe was not silent in the ordinary sense. Of course, it was unimaginably energetic, violent beyond description, temperatures so extreme that matter itself struggled to exist in stable forms. But there were no observers, no ears, no worlds, no oceans to carry sound, only expansion, only energy cooling and spreading through newborn space. When people hear the phrase Big Bang, they often imagine an explosion happening somewhere in empty darkness, like fireworks going off in space. But that picture is misleading. The Big Bang was not an explosion inside the universe. It was the rapid expansion of space itself, everywhere expanding at once. No center, no edge, no cosmic fireball sitting in the middle while debris flew outward. And for a while, the universe was too hot for atoms to even exist properly. That detail matters more than it sounds. Imagine trying to build something delicate while standing inside a blast furnace. Electrons could not settle down around nuclei because the temperatures were simply too intense. Matter existed as a dense plasma, glowing brilliantly but also trapping light completely. In those earliest ages, the universe was opaque. Light existed, certainly huge amounts of it, but photons could barely travel any distance before crashing into charged particles. The cosmos was like an endless fog made of pure energy. Then gradually, over hundreds of thousands of years, things cooled enough for atoms to finally form. This moment is called recombination, which sounds oddly like a corporate merger between very enthusiastic chemistry departments, but it marks one of the great turning points in cosmic history. Once electrons settled into stable atoms, light suddenly gained freedom. The fog lifted. Photons began traveling across the universe uninterrupted. Some of that ancient radiation still exists today. We call it the cosmic microwave background, the oldest light we can directly observe, a faint afterglow from the infant universe itself. And after that light spread outward, something curious happened. Darkness returned. Not complete darkness, perhaps, but something close enough that modern astronomers gave it an appropriately dramatic name. The Cosmic Dark Ages. This period lasted for millions upon millions of years. No stars yet, no galaxies, only vast clouds of hydrogen drifting through expanding space. It's difficult for modern humans to picture because our skies are crowded with structure. Even on a cloudy night above a city, there are satellites, airplanes, distant streetlights reflecting off the atmosphere. Complete emptiness feels unnatural to us. But the young universe spent an astonishingly long time waiting for gravity to begin assembling the first great structures. Gravity, meanwhile, was already hard at work. Tiny fluctuations in matter density left over from the early universe began growing slowly over time. Regions with slightly more matter pulled in additional matter. Bit by bit, clouds formed, then larger clouds, then denser regions. Gravity is patient like that. It does not rush. Give it enough time, and even thin gas drifting through space can become stars, galaxies, clusters, and eventually planets covered in creatures who stay awake at midnight, wondering about ancient galaxies with impossible names. The first stars likely appeared around 100 to 200 million years after the Big Bang. That sounds ancient to us, but cosmologically speaking, it happened remarkably quickly. And these first stars were probably very different from the stars we see today. Modern stars contain heavier elements like carbon, oxygen, silicon, and iron, because earlier generations of stars created those materials through nuclear fusion. But the first stars had almost none of that. The universe initially contained mostly hydrogen and helium, with trace amounts of lithium. That means the earliest stars may have grown enormous. Some models suggest they reached hundreds of times the mass of our Sun. Huge, hot, short-lived, and incredibly bright. These stars burned through their fuel rapidly and exploded violently, enriching the universe with heavier elements for the first time. Without those early stars dying, planets like Earth could never form. Your bones contain calcium forged inside ancient stars. The iron in your blood was created through stellar processes billions of years ago, which means this story about ancient galaxies is also quietly a story about you. Not metaphorically, literally. Every atom in your body has cosmic ancestry. And somewhere during this era of first stars and violent formation, the earliest galaxies began emerging from the darkness, small at first, chaotic, nothing like the elegant spirals we associate with galaxies today. Modern galaxies look organized because they've had billions of years to evolve. Early galaxies were messy places, gas clouds colliding, stars forming rapidly, radiation blasting through turbulent regions, matter still assembling itself into recognizable structures. The young universe was not calm. It was busy becoming itself. For decades, astronomers tried to push farther back into this ancient era, using increasingly powerful telescopes. Every new instrument revealed older galaxies, older stars, more distant objects, but eventually they reached a frustrating limit. The universe itself was hiding its earliest history from us, partly because distant galaxies are extremely faint. Their light stretches as the universe expands, shifting toward longer wavelengths in a process called redshift. This happens because space itself expands while light travels through it. Imagine drawing waves on a balloon, then inflating the balloon. The waves stretch farther apart. Light behaves similarly across expanding cosmic distances. By the time ancient light reaches Earth, wavelengths originally emitted as visible or ultraviolet light may arrive as infrared radiation. And Earth's atmosphere is rather annoying about infrared observations, useful for breathing, less helpful for ancient cosmology. So astronomers needed something new, something colder, something far from Earth, something capable of detecting extremely faint infrared light from the edge of cosmic history. For years, people talked about the successor to the Hubble Space Telescope, almost like it was a scientific myth, an impossibly ambitious machine requiring technologies never before attempted at such scale. The project faced delays, budget problems, engineering nightmares. At one point, it reportedly required over 300 single-point failure risks to work correctly during deployment, meaning hundreds of things that absolutely could not fail, which is not the sort of statistic that helps engineers sleep peacefully. The telescope eventually became known as the James Webb Space Telescope, and unlike Hubble, Webb was designed specifically to see deeper into infrared wavelengths, deeper into the ancient universe, deeper into time itself. Because looking far away in space is also looking backward in time. That idea deserves a moment to settle in properly. Nothing we see exists exactly as it is now. Moonlight is already over a second old when it reaches Earth. Sunlight takes about 8 minutes to arrive. The nearest star beyond the Sun appears to us as it existed more than 4 years ago, and distant galaxies appear millions, billions, sometimes over 13 billion years in the past. Astronomy is fundamentally an act of historical observation. Telescopes are our time machines, not metaphorically, but physically. Every improvement in telescope technology extends humanity's view farther backward across cosmic history, and Webb was built for exactly that purpose. When it finally launched in December 2021, there was enormous tension surrounding the mission. Webb's folded mirror and tennis court-sized sunshield had to deploy perfectly in space. No astronauts could repair it easily. Unlike Hubble, Webb orbits far beyond the Moon near a gravitational balance point called L2. If something failed, that would likely be the end. So engineers watched anxiously as the telescope unfolded piece by piece across space. Mirror segments aligned, sunshield deployed, systems cooled, instruments activated, and then Webb began looking outward. What happened next surprised even many astronomers. The early universe appeared brighter, more active, and more crowded with galaxies than expected, not gradually evolving into complexity over enormous timescales, but seemingly assembling large structures very quickly. And among the astonishing discoveries emerging from Webb observations was one faint ancient galaxy, buried deep inside a survey called jades. Jades stands for the JWST Advanced Deep Extragalactic Survey, a name far less catchy than oldest galaxy in the universe, admittedly, but astronomers do love their acronyms. Inside this survey, researchers identified an object with an astonishing red shift value around 14, meaning we are seeing it as it existed only about 290 million years after the Big Bang. That is incredibly early. The universe at that point was barely beginning its long history. Earth today is about 4.5 billion years old. This galaxy's light began travelling toward us almost 9 billion years before our planet existed. Dinosaurs were still absurdly far in the future. Continents did not exist. Nothing human, even remotely imaginable, existed. And yet the light survived across expanding space, across cosmic evolution, across the formation of galaxies, stars, planets, oceans, civilizations, languages, telescopes, and sleepy videos, until finally one species, on one small world, looked upward and noticed it. There is something deeply calming about that. The universe does not hurry. Galaxies are born, stars die, light travels for billions of years without complaint. Meanwhile, humans become impatient, waiting for elevators. Perspective can be wonderfully relaxing sometimes. Still, the discovery of jades GS Z140 did more than simply break records. It raised difficult questions because, according to many earlier models, galaxies this bright and developed should not have existed so soon after the Big Bang. The young universe may have formed structure faster than scientists predicted. And whenever the universe behaves differently than expected, astronomy becomes especially interesting. Scientists love being correct, of course, but discoveries become truly exciting when nature quietly says, actually, it's a little stranger than you thought. That strange possibility is part of what makes Webb's discoveries feel so important. We're not merely filling in details. We're entering territory where our understanding itself may need adjustment. And perhaps that is fitting. After all, every generation thinks it understands the cosmos fairly well, right before the universe casually reveals something enormous hiding in the darkness. In the centuries ahead, humans may discover galaxies even older than JD's GS Zhao Webb itself may uncover more ancient structures still waiting quietly at the edge of visibility. Perhaps someday another telescope will look farther back yet, toward the first stars themselves, toward the moment the cosmic darkness first began breaking apart. Try to imagine a universe without stars for a moment, not a cloudy night sky where the stars are hidden behind weather, not a city sky washed pale by streetlights and glowing windows. A universe genuinely without stars, no galaxies hanging in the distance, no planets, no constellations, no familiar points of light at all. Only darkness gradually unfolding across expanding space. It feels strange because our brains are used to structure. Humans naturally organize the sky into patterns. We connect stars into hunters and bears and mythological creatures carrying swords for reasons nobody fully questions anymore. We name galaxies, we label nebulae. We divide the cosmos into understandable pieces because our species is deeply uncomfortable with enormous unnamed emptiness. But there was a time before any of that existed. Long before galaxies had names, before galaxies had shapes, before galaxies properly had identities at all, the universe was still trying to become a place where such things were even possible. And oddly enough, the story starts with conditions so extreme that almost every normal human comparison completely fails. To understand the conditions that birthed JD's GS Xeon 0, we must look directly into the physics of the primordial furnace. In the initial fractions of a second following the expansion of space, the cosmos was entirely uniform, packed with an unimaginably dense, blistering plasma that defied any structural organization. The heat was so incredible that subatomic particles could not bind together. Protons and neutrons were subjected to a relentless kinetic bombardment that prevented them from forming the very first atomic nuclei. This meant that the universe, in its infancy, lacked any chemical identity whatsoever. It possessed no elements, no molecules, and no chemistry. It was a fluid ocean of pure, high-energy potential, expanding and cooling across the newborn dimensions of space-time. As the minutes progressed, the temperature of the expanding cosmos dropped below the threshold of absolute atomic disruption. This specific window of cooling allowed a process known as Big Bang nucleosynthesis to occur. Within this brief cosmic window, protons and neutrons finally bound together to forge the absolute lightest elements on the periodic table. Vast quantities of hydrogen ions were established, alongside a significant proportion of helium nuclei and minuscule trace quantities of lithium. This simple chemical mixture became the primary material of the universe. It was the foundational ingredient list from which every subsequent star, galaxy, planet, and living organism would eventually be assembled over billions of years. However, even though these fundamental nuclei now existed, they remained completely decoupled from electrons due to the lingering ambient heat. the universe was still a completely ionized plasma, a brilliant white fog, where free electrons continuously scattered photons in every conceivable direction. A particle of light could not travel for more than a microscopic fraction of a second before colliding violently with an electron, trapping the radiation entirely within the dense plasma fluid. Because of this eternal scattering, the early universe was completely opaque. If an observer had been present, they would have been surrounded by an all-encompassing, blinding wall of light, yet they would have been entirely unable to see any distinct structures, shapes, or distant objects. This brilliant, opaque epoch persisted for approximately 380,000 years. During this immense stretch of time, the cosmos did nothing but silently expand and grow progressively cooler. When the ambient temperature finally fell to roughly 3000 Kelvin, the kinetic energy of the free electrons dropped below the binding energy of the hydrogen and helium nuclei. In an instant that rippled across the entirety of space, electrons fell into stable orbits around the waiting nuclei, neutralizing the plasma and forming the very first neutral gas atoms. This monumentally peaceful transition, known to science as recombination, altered the physical properties of the universe forever. With the free electrons suddenly locked safely inside neutral atoms, the cosmic fog vanished completely. Photons that had been trapped in an eternal cycle of scattering were suddenly liberated, finding themselves traveling through a perfectly transparent vacuum. This first free radiation poured out across the newly cleared dimensions of the cosmos, embarking on an eternal journey that continues to this very day. As this ancient light travelled through an expanding universe over the next 13.8 billion years, its wavelengths were steadily stretched by the expansion of space-time itself, cooling from a blinding glare down into a faint, invisible whisper of microwave energy that coats the entire sky. We detect it today as the cosmic microwave background, a perfect photographic snapshot of the universe at the exact moment it became transparent. Once this primordial flash of light escaped into the infinite distance, a strange and quiet transformation took hold of the universe. As the primordial gas expanded outward, it grew steadily cooler and darker. Because there were no stars, no burning cores, no glowing nebulas, and no active galaxies to illuminate the vast expanses of space, the cosmos entered the prolonged era known as the Cosmic Dark Ages. For millions of years, the universe was an immense, silent, and completely black desert, filled with nothing but cold, invisible clouds of neutral hydrogen and helium gas, drifting aimlessly through an ever-growing void. It was a time of absolute stillness and profound patience, where the future architecture of reality existed only as a hidden potential waiting for the slow, relentless work of gravity. To our human minds, which are completely dependent on the rapid pacing of daily life and the vibrant light of our local sun, this prolonged era of total darkness feels incredibly alien. We struggle to visualize a reality where absolutely nothing shines. Yet, this period of waiting was absolutely essential for the eventual birth of complex structures like jades, GS, zeta in 0. If the early universe had been perfectly smooth, the gas would have expanded uniformly forever, thinning out until the cosmos became a permanent, featureless void. But the universe was not perfectly smooth. Microscopic quantum fluctuations that had been stretched across space during the initial expansion left behind incredibly subtle variations in the density of the primordial gas. Some regions of space contained a fraction of a percent more hydrogen atoms than the surrounding areas. This tiny, almost imperceptible difference gave these specific regions a slightly stronger gravitational pull than the emptier voids around them. Gravity began its monumental slow-motion labour, quietly drawing nearby gas atoms into these shallow gravitational wells. It was a process that required millions of years of patient accumulation. Bit by bit, the slightly denser pockets of gas grew heavier, which in turn increased their gravitational authority, allowing them to pull in even more material from the surrounding space. As these primordial clouds slowly collapsed under their own immense weight, their internal pressures and temperatures began to climb. The atoms at the centers of these collapsing gas spheres were pressed closer and closer together, colliding with increasing velocity. This slow motion compression marked the final act of the cosmic dark ages. The cold, dark gas clouds were transforming into cosmic crucibles, preparing to ignite the very first generation of stars and break the absolute monopoly of the dark ages. And it was within these massive accumulating centers of gas that the earliest seeds of the very first galaxies were quietly being planted, setting the stage for the dramatic appearance of ancient stellar cities like Jades, GS, Z410. To fully understand how cities of stars like Jades, GS, Z140 managed to form so quickly, we have to look closely at the behavior of the very first generation of stars. These primordial objects, known to astrophysicists as population 3 stars, were completely different from any star we can see in our night sky today. Modern stars are chemically enriched with heavier elements, but these pioneer stars were made of pure, unadulterated primordial gas. Because the early universe lacked carbon, oxygen, or iron to help radiate heat away efficiently during the collapse of the gas clouds, the clouds had to become incredibly massive before gravity could overcome internal pressure. This physical dynamic meant that the first stars grew to gargantuan sizes, often reaching hundreds of times the mass of our local sun. They were massive, luminous, short-lived titans that burned with an intense blue-white glare, blasting the surrounding darkness with a fierce torrent of ultraviolet radiation. Because these massive stars were so incredibly large, their internal nuclear furnaces operated at extreme temperatures and pressures. They did not have the patience to burn steadily for billions of years like our gentle sun. Instead, they tore through their immense reservoirs of hydrogen and helium fuel in just a few million years. During their brief, intense lifespans, their cores fused the light primordial elements into heavier elements for the very first time in cosmic history. Carbon, nitrogen, oxygen, and silicon were forged in the centers of these brilliant giants. When their fuel was completely exhausted, they did not fade away quietly. They collapsed rapidly and exploded as hypernovae, colossal stellar detonations that were far more energetic than a typical supernova. These massive explosions scattered the newly forged elements far and wide across the surrounding gas clouds. This marked the absolute end of the chemical innocence of the universe. The presence of even a tiny fraction of a percent of these heavier elements completely changed how subsequent gas clouds behaved. The heavy elements allowed the gas to cool down much more efficiently, meaning that the next generation of clouds could fragment into much smaller, more manageable pieces. This cooling efficiency allowed for the birth of smaller, longer-lived stars, the very types of stars that could gather together over long periods to build stable, long-lasting galactic structures. Without the rapid life cycles and violent deaths of those first blue titans, the universe would have remained a cold, chemically primitive desert where complex worlds and life could never emerge. As these hypernova explosions seeded space with heavy elements, the immense gravitational fields of dark matter were simultaneously pulling these enriched gas pockets together. Dark matter, the invisible scaffolding of the universe, had formed massive halos long before regular matter could settle down. These dark matter halos acted as massive gravitational nets, catching the drifting gas and the newborn stars. Inside these deep gravitational wells, the chaotic dance of galactic assembly began in earnest. Smaller stellar clusters were drawn toward one another, colliding and merging in a continuous turbulent process. This was the turbulent environment that allowed Jades GS Z140 to take shape, growing rapidly by absorbing nearby gas streams and smaller groups of stars. The young universe was a place of extreme proximity and rapid interaction. Because space itself was significantly smaller back then compared to its current expanded state, everything was packed much closer together. Gas clouds collided with immense frequency, creating powerful shock waves that compressed the hydrogen and triggered intense bursts of new star formation. This rapid pacing meant that early galaxies could accumulate mass at a speed that completely blindsides modern computer simulations. They were not growing through the slow, gentle accumulation of isolated stars over billions of years. They were forged in a highly active cosmic crucible, where immense forces worked together to build complex structures in a fraction of the time scientists previously thought possible. This brings us back to the incredible discovery made by the James Webb Space Telescope. When astronomers first looked at the data for jades GS Z14-0, they were looking for a tiny, barely discernible spark of light. Instead, they found a galaxy that was remarkably bright and structurally expansive for its age. The object was not a primitive, loosely bound cloud of a few hundred stars. It was a fully realized galactic system stretching across thousands of light years, containing hundreds of millions of stars that were already pouring out immense amounts of energy into the surrounding space. This structural maturity is what makes the galaxy so profoundly puzzling for modern astrophysics. To determine the exact age and distance of this ancient system, scientists had to use a highly precise technique known as spectroscopy. They could not simply rely on a standard photograph. A photograph can show that an object is red, but it cannot definitively prove whether that redness comes from extreme distance, or if the object is simply a nearby, naturally red star or dust cloud. Spectroscopy avoids this ambiguity by breaking the incoming light down into its individual component wavelengths, creating a highly detailed cosmic barcode. Every chemical element leaves behind a very specific pattern of lines on this barcode, allowing scientists to see exactly what materials are inside the galaxy and how much those lines have been shifted toward the red end of the spectrum by the expansion of the universe. When Webb's near-infrared spectrograph spent hours collecting photons from JD's GS-Z410, it revealed a clear, definitive signature. The Lyman alpha break, a sharp drop-off in the galaxy's light spectrum caused by neutral hydrogen gas absorbing ultraviolet radiation, was shifted to a degree that confirmed a red shift of 14.32. This value mathematically locks the galaxy into a period just 290 million years after the Big Bang. It is an empirical data point that cannot be easily explained away or dismissed as a measurement error. The barcode was clear, precise, and completely verified by independent teams of researchers around the world. But the spectrum revealed something even more shocking than the raw distance. When scientists examined the specific lines within the infrared barcode, they detected the clear, unmistakable signature of oxygen gas. Think about the profound implications of that finding. Oxygen does not come from the Big Bang. The Big Bang only produced hydrogen, helium, and a tiny bit of lithium. For oxygen to exist inside JD's GS Z14-0, just 290 million years after the beginning of time, entire generations of massive stars must have already been born, lived out their lives, synthesized oxygen in their cores, and exploded to scatter that oxygen into the interstellar medium. This single chemical signature proves that JD's GS Z14-0 was not the very first thing to form in the darkness. It was already a mature product of a previous hidden history. It means that even farther back in time, deeper into the dark ages, the very first stars were working at an incredible pace, transforming the pristine primordial gas into a complex chemical soup before this galaxy even assembled. Every discovery pushes the boundary back further, revealing that the infant universe was far more sophisticated, active, and efficient at building complexity than our current scientific models ever anticipated. To understand the immense challenge that astronomers faced before the era of modern space telescopes, we have to look closely at the physical limitations of observing the deep cosmos from the surface of our planet. For decades, the Hubble Space Telescope pushed the boundaries of human vision, capturing breathtaking images of distant galaxies that fundamentally reshaped our understanding of the universe's structure. Hubble was an incredible machine, but it had a fundamental limitation built directly into its design. It primarily observed the universe in visible and ultraviolet light wavelengths. When scientists attempted to use Hubble to look even farther back in time, toward the very first generation of galaxies, they ran directly into an inescapable physical barrier caused by the expansion of space itself. This barrier is a phenomenon known as cosmic redshift, a foundational concept in modern cosmology that sounds highly technical but can be understood through a simple physical analogy. Imagine taking a regular rubber balloon and drawing a series of neat, tight light waves across its surface with a marker. If you take a deep breath and begin to inflate the balloon, the physical material of the balloon stretches outward in every direction. As the surface expands, the waves you drew are pulled along with it, stretching out until the distance between each wave becomes significantly larger. Light behaves in exactly the same manner as it travels across the vast expanses of our expanding cosmos. When an ancient galaxy like Jades GS Z14 first emitted its light billions of years ago, that radiation was energetic and short, falling squarely within the ultraviolet and visible spectrums. But as those photons embarked on their multi-billion-year journey toward Earth, the very space they were traveling through was continuously expanding. This relentless stretching of space-time pulled at the light waves, steadily lengthening their wavelengths. By the time this ancient radiation finally arrived in our solar system, its wavelengths had been stretched so significantly that they had shifted completely out of the visible spectrum and deep into the longer invisible wavelengths of infrared radiation. This physical transformation created a massive obstacle for ground-based astronomy, because Earth's atmosphere is incredibly problematic when it comes to observing infrared light. While our thick atmosphere is absolutely essential for human life, protecting us from lethal radiation and providing the oxygen we need to breathe, it acts as a thick, nearly impenetrable blanket to incoming infrared photons from deep space. Water vapor, carbon dioxide, and other gases in the air absorb and scatter infrared wavelengths, effectively washing out the incredibly faint heat signatures of the earliest structures in the universe. To see the dawn of cosmic history, humanity had no choice but to build a new kind of observatory, one that could leave the atmosphere behind entirely and sit in the cold, pristine vacuum of space. This ambitious vision eventually led to the creation of the James Webb Space Telescope, a machine that for many years felt less like a real engineering project and more like a scientific myth. The scale and complexity of the telescope required technologies that had never been attempted, let alone tested in the unforgiving environment of space, because the telescope needed to detect the faintest whispers of infrared heat from the edge of the observable universe. The entire spacecraft had to be kept at temperatures just a fraction above absolute zero. If the telescope's own components warmed up even slightly, their native thermal radiation would completely blind the ultra-sensitive detectors, ruining any chance of seeing ancient galaxies. To achieve this extreme cooling, engineers had to design a massive 5-layer sunshield, the size of a tennis court, made of a specialized material called kapton. This shield had to deploy perfectly in space, acting as a permanent umbrella to block the blistering heat and light of both the sun and the Earth. Furthermore, because the telescope's massive primary mirror was too large to fit inside the payload fairing of any existing rocket, it had to be constructed as a complex origami structure composed of 18 hexagonal, gold-coated beryllium segments that would unfold autonomously once in orbit. The sheer number of moving parts introduced unprecedented engineering risks, with over 300 single-point failures built into the deployment sequence. If a single one of these mechanical systems failed to operate exactly as planned, the entire multi-billion-dollar project would be left as a useless piece of space debris. The project faced decades of severe delays, compounding budget issues, and intense political scrutiny that nearly led to its cancellation. The engineers and scientists working on Webb spent years plagued by sleepless nights, knowing that they were building a machine that could not be repaired by astronauts if something went wrong. Unlike Hubble, which orbited comfortably just a few hundred miles above Earth and could be serviced by the space shuttle, Webb was destined for a unique orbit far beyond the path of the Moon. Its destination was the second Lagrange point, or L2, a special gravitational balancing point located roughly 1.5 million kilometers away from Earth. At this immense distance, Webb would be entirely on its own, drifting in a permanent orbit that kept the Earth and Sun aligned perfectly behind its protective sunshield. When the telescope finally launched on Christmas Day in 2021, a collective breath was held across the global scientific community. Over the subsequent weeks, as the spacecraft traveled toward L2, engineers watched in agonizing suspense as the telescope unfolded itself piece by piece in deep space. The sunshield tensioned perfectly, the primary mirror wings swung into place and locked, and the active cooling systems began lowering the temperature of the instruments to their required cryogenic states. Once the mirror segments were aligned with microscopic precision, Webb finally turned its golden eye toward the deepest darkness of the cosmos and began gathering light. The very first observations that returned from the telescope completely blindsided the astronomical community. According to decades of carefully constructed theoretical models, the early universe was supposed to be a sparse, dim environment where small pockets of gas were only beginning to slowly gather into primitive structures. Astronomers expected to see a gradual, highly measured evolution toward complexity over vast spans of cosmological time. Instead, Webb's deep field images revealed an early cosmos that was remarkably bright, highly active, and heavily crowded with fully formed galaxies. The infant universe was building massive, luminous structures with an efficiency that challenged existing cosmic timelines. It was within this surprising, hyperactive landscape that scientists identified the faint ancient signal of jades GS 0110. The galaxy was detected as part of the JWST Advanced Deep Extragalactic Survey, an ambitious multi-instrument research project abbreviated by astronomers as JADES. While the formal title lacks the immediate dramatic flair of a public headline, the survey itself represents the absolute pinnacle of human deep space observation. To find these hidden treasures, the telescope had to pick out small, seemingly empty patches of the night sky, regions that had been studied for years by older telescopes, and stare into them with immense patience, accumulating faint infrared photons over long exposure times. This methodology highlights one of the most beautiful and quiet truths about modern astronomy. Progress is fundamentally built on patience. The universe does not reveal its deep historical secrets quickly or dramatically. Instead, ancient photons that have been traveling through the void for over 13 billion years arrive at Webb's detectors one by one, slowly depositing their tiny packets of energy onto the ultra-cold sensors. Over many hours of continuous integration, these microscopic signals accumulate, gradually building a discernible picture out of the baseline cosmic noise. A distant galaxy from the dawn of time does not announce its presence with a sudden flare. It emerges quietly, appearing as a soft, unassuming dot against the background darkness. When researchers first looked at the raw image data containing JADES GS Z140, it looked completely unremarkable to an untrained eye. It did not feature the majestic, sweeping spiral arms or the elegant, glowing dust lanes that define mature galaxies closer to home. Instead, it was a tiny, faint reddish smudge, just a few pixels wide, buried deep within a dense field of thousands of other distant objects. Yet the precise shade of red and the specific way the object disappeared in shorter wavelengths hinted at something extraordinary. This tiny smudge possessed a record-breaking redshift value near 14, providing empirical proof that humanity was looking at a massive city of stars as it existed a mere 290 million years after the Big Bang. The physical properties of this record-holding galaxy force cosmologists to re-evaluate their baseline assumptions regarding the pace of early cosmic structural formation. Under traditional galactic growth models, an object located at such an extreme redshift distance should exhibit clear signs of structural simplicity and chemical immaturity. Scientists expected that any systems found within the initial 300 million years of space-time would resemble small, loose, unstructured collections of primordial gas containing only a few thousand newly ignited stars. They anticipated finding chaotic, dwarf-sized, star-forming clumps, rather than expansive, highly organized, and luminous galactic architectures. However, the empirical spectroscopic data collected from JADES GS Z140 revealed a completely different physical reality. The galaxy is remarkably large, possessing a physical diameter that spans several thousand light years across. This indicates that the system had already succeeded in accumulating hundreds of millions of solar masses worth of ordinary baryonic matter within a remarkably compressed time frame. The sheer volume of stars required to generate the level of intrinsic brightness detected by the James Webb Space Telescope indicates a hyper-accelerated rate of star birth that completely outpaces standard theoretical expectations. To account for this intense luminosity, astrophysicists must look at the rate of star formation inside the primordial gas reserves. In our mature, modern universe, a typical galaxy like the Milky Way experiences a highly measured, steady rate of star production, averaging roughly 1 to 2 new solar masses per year. This slow pacing occurs because modern galactic environments contain stable magnetic fields and warm gas reserves that collapse very gradually over immense timelines. The gas clouds can remain in hydrostatic equilibrium for millions of years before a passing shockwave triggers a localized collapse. In stark contrast, the environment surrounding jades GS Z140 was operating at a level of extreme, relentless activity. The data indicates that this ancient system was converting its dense hydrogen reservoirs into massive new stars at a rate that was dozens of times higher than anything observed in stable modern galaxies. This extreme starburst activity was happening simultaneously across the entire width of the young galactic core. The system was essentially a massive stellar factory, rapidly turning pristine gas into brilliant clusters of blue stars that flooded the newborn space with a torrent of ionizing ultraviolet light. This hyper-efficient generation of stars introduces a major theoretical puzzle regarding the feedback mechanisms of early star formation. In modern astrophysics, when a massive cluster of new stars ignites, it generates incredibly powerful stellar winds and intense radiation pressure. This outward force typically acts as a natural brake, blowing away the surrounding reservoirs of cold gas and effectively cutting off the supply line required to sustain star birth. This negative feedback loop ensures that galaxies regulate their own growth, preventing them from consuming all of their star-building materials in one sudden, unsustainable flash. Yet JD's GS Z4410 managed to completely bypass or overcome this regulatory feedback loop. The galaxy continued to form stars at an incredible pace, despite the immense outward pressure generated by its own newborn stellar populations. This indicates that the localized gravitational potential, driven by dense accumulations of both ordinary matter and invisible dark matter, was so overwhelmingly strong that it could hold on to the gas reserves, forcing them to continuously collapse downward into the core, despite the violent radiation pushing outward. This deep gravitational trapping brings us back to the vital role played by dark matter in the early timeline of the universe. Because dark matter does not interact with electromagnetic radiation, it was completely unaffected by the extreme heat that kept regular matter ionized and scattered during the initial 380,000 years following the Big Bang. While protons and electrons were still trapped in the blinding plasma fog, unable to settle into structures, dark matter was already actively responding to the pull of gravity. It quietly condensed into immense localized halos across the dimensions of space, forming a massive, invisible network of structural wells. When the universe finally reached the moment of recombination and cooled down enough for neutral hydrogen atoms to form, this regular gas found itself surrounded by a fully formed gravitational landscape. The gas did not have to start from scratch to build structures. It simply slid down into the pre-existing dark matter wells, like rainwater, pooling into deep valleys on a mountainside. The immense mass of these dark matter halos provided the extreme gravitational pressure needed to force the pristine gas into hyperdense configurations, accelerating the timeline of structural collapse and allowing systems like JD's GS Z410 to achieve their unexpected size and maturity so quickly. To verify that this unexpected brightness was driven entirely by star formation and not by alternative cosmic phenomena, astronomers had to carefully investigate another fascinating possibility. When a galaxy appears remarkably luminous at an extreme distance, the brightness can sometimes be amplified by the presence of an active galactic nucleus, or quasar. A quasar occurs when a supermassive black hole sitting at the absolute center of a galaxy violently feeds on infalling gas. As the gas spirals inward toward the event horizon, it forms a dense accretion disk that rubs against itself at relativistic speeds, generating intense friction that releases unbelievable amounts of bright energy across the electromagnetic spectrum. If Jades GS Z14-0 hosted a massive hyperactive central black hole, a substantial portion of its detected light would be coming from a single point-like source at its center, rather than from the collective glow of millions of individual stars spread out across the galaxy. To distinguish between these two scenarios, scientists used the James Webb Space Telescope's high-resolution imaging capabilities to map the spatial distribution of the light. If the light were coming entirely from a feeding black hole, the object would look perfectly sharp and compact, appearing as a singular, point-like beacon. The spatial analysis revealed that the light was distinctly extended and diffuse. The brightness was not concentrated into a single microscopic point. It was distributed across an expansive region, measuring several thousand light-years in diameter. This physical profile provided definitive confirmation that the primary engine driving the galaxy's immense luminosity was indeed a vast distributed population of young stars. We are looking at the collective glare of hundreds of millions of suns burning simultaneously across a young galactic disk, providing an authentic look at an entire stellar ecosystem operating at the absolute dawn of history. To fully comprehend the deep, profound irony of human existence, we must realize that our capacity to study these primordial galactic structures exists despite the reality that humanity arrived incredibly late in cosmic history. We are a very young species looking back at an old world. To put our sudden arrival into an understandable perspective, scientists often employ a standard thought experiment where the entire 13.8 billion year history of the cosmos is compressed down into a single standard 12-month calendar year. On this cosmic calendar, the dramatic event of the Big Bang occurs precisely at the very first microsecond of January 1st. As we slide through this compressed timeline, months pass in complete silence, while gravity works to assemble the first stars and early systems like Jades GS Z14-0 during the later weeks of January and early February. Our own solar system and the planet we call home do not even form until late August or early September. Complex biological life begins to crawl out of Earth's oceans only in December. Where do human beings sit on this vast scale? All of recorded human history, from the construction of the ancient pyramids to our modern space programs, is compressed into the final seconds before midnight on December 31st. Every kingdom, every war, every book written, and every language spoken exists exclusively within those last few fleeting seconds of the cosmic year. This staggering realization means that everything humans have ever built or conceptualized exists as a microscopic afterthought on the grand timeline of space-time. Yet, from our brief vantage point in the final seconds of the cosmic calendar, we have managed to build sophisticated tools capable of peering back to the very beginning of that calendar year. This creates a beautiful contrast. We are small, fragile creatures tied to a tiny planet, yet our minds can span the entire breadth of space and time. We can read the ancient light signatures of a universe that was busy becoming itself long before our world was even a remote possibility. Before the deployment of the James Webb Space Telescope, our standard theoretical models describe the early stages of this timeline as a very slow, gradual process. The general consensus among astronomers was that primordial matter required vast amounts of time to coordinate into structures. The earliest pockets of gas were expected to pull together very hesitantly, forming tiny, primitive galaxies that would merge over billions of years to create larger, organized structures. Scientists widely assumed that the universe during its first few 100 million years was relatively sparse and dim, lacking the efficiency to assemble anything complex. This gradual view of cosmic evolution made intuitive sense. Astronomers compared the process to building a massive modern metropolis immediately after inventing the very first brick. While you might understand the basic mechanics of stacking bricks together, it remains physically impossible to construct a fully functioning city with skyscrapers overnight. The young universe was thought to face similar structural constraints. Stars required time to condense. Gravity required time to draw diffuse gas across millions of light years. And the first generations of massive stars needed to complete their life cycles to seed space with the heavier elements necessary for advanced cosmic chemistry. But when Webb opened its golden eye and delivered its initial deep field datasets, this neat gradual model was immediately challenged by reality. The discovery of highly developed luminous galaxies, like jades GS-Z0 forced scientists to acknowledge that the early cosmos was operating under a much more aggressive timeline than anyone had anticipated. The universe was not waiting politely for billions of years to develop complexity. It was building massive, star-filled cities with astonishing speed and efficiency. This realization has completely reshaped humanity's understanding of cosmic history, transforming our view of the early universe from a cold, barren void into a dynamic and highly productive environment. It shows that the laws of physics are naturally wed to favor rapid self-organization under the high-density conditions of the infant cosmos. When matter is tightly packed together and gravity is given even the slightest variation in density to work with, structure does not emerge hesitantly, it explodes into existence. This brings us to a fundamental property of light that governs all of observational astronomy, the fact that light requires time to travel across space. Because the speed of light is a fixed cosmic constant, the cosmos remains partly hidden from us, revealing its history in a series of delayed signals. When we look out into the night sky, we are never seeing the universe as it exists in our current shared moment. Instead, we are looking at a complex mosaic of different historical eras, all layered on top of one another. To understand this concept deeply, we must recognize that every telescope built by human hands functions fundamentally as a physical time machine. When you look up at the moon on a clear night, you are seeing it as it existed 1.3 seconds ago, because that is how long it takes for moonlight to cross the distance to Earth. Sunlight takes roughly 8 minutes to reach our planet, meaning if the sun were to magically turn off right now, we would continue to see its warm glow for 8 full minutes before darkness arrived. The nearest star system beyond our sun, Alpha Centauri, is seen not as it is today, but as it looked more than 4 years in the past. When we extend this physical rule across the vast expanses of the deep cosmos, the timelines become truly mind-boggling. The distant galaxies captured in Webb's deep field images are seen as they existed millions, billions, or even 13.5 billion years ago. Therefore, when astronomers study JD's GS-Z0, they are observing an authentic snapshot of the infant universe. The ancient photons that left that galaxy spent over 13 billion years traveling through the vacuum of space, carrying a pristine visual record of a structure that existed when the universe was only a fraction of its current age. This creates a fascinating paradox, because the galaxy we are observing in Webb's data almost certainly no longer exists in that form today. During the 13.5 billion years it took for that light to reach our modern detectors, the galaxy itself continued to evolve, merge, and transform. Its original populations of massive blue stars burned through their fuel and exploded long ago, seeding the system with heavy elements. Over cosmic time, JD's GS-Z-0 likely collided with neighboring systems, merging into a massive, organized spiral or elliptical galaxy that looks completely unrecognizable compared to the small, intense smudge we see in our telescopes. Yet, because the newer light from those later stages of evolution is still traveling through space, humanity is permanently locked into seeing the galaxy's infancy. We are looking at a ghost from the dawn of time, an object that has already lived its entire life, changed its shape, and perhaps faded away, but whose childhood is just now arriving on our doorstep. This is the beautiful, haunting nature of deep space astronomy. The farther we look into the distance, the closer we get to the absolute origin of everything. Every increase in our observational power allows us to peel back another layer of cosmic history, pushing humanity closer to the boundary where the Dark Ages ended and the very first light switched on. To fully understand the long journey this light took to reach us, we must explore what happened to the universe during those billions of years. While the photons from jades GS Z14-0 were traveling through space, the surrounding cosmos was changing completely. It was entering a massive transformative stage known to science as the epoch of rayonization. This specific era represents another huge turning point in cosmic history, when the neutral gas filling space was systematically transformed by the energy of the very first stars and galaxies. As we discussed earlier, the universe became neutral during the recombination era, leaving behind vast cold clouds of regular hydrogen gas that filled the void. This neutral gas was highly efficient at absorbing ultraviolet light. This meant that when the earlier stars and small galaxies first ignited, their brilliant radiation could not travel very far through space. The young universe was essentially filled with a thick cosmic fog of neutral hydrogen. Any ultraviolet photons leaving a newborn star would quickly slam into a nearby hydrogen atom, getting absorbed and heating the gas rather than traveling into the distance. But as more and more galaxies began to assemble, the sheer volume of ultraviolet light increased dramatically. Systems like jades GS Z10 were acting as cosmic heaters, continuously pumping out immense amounts of high-energy radiation. When these energetic photons hit the surrounding, neutral hydrogen atoms, they did not just get absorbed blindly. They hit with enough kinetic energy to strip the electrons completely away from the proton nuclei. This physical process is what scientists call ionization, turning neutral atoms back into charged plasma particles. Initially, this ionization happened in small isolated pockets around the brightest galaxies, like bubbles of clear air forming inside a thick morning fog. Inside these growing bubbles, the gas became fully ionized, allowing ultraviolet light to travel freely without getting blocked. As the millions of years rolled on and more star cities formed, these isolated bubbles expanded steadily outward across space. They began to touch, overlap, and merge, slowly clearing the thick fog out of the cosmic landscape. By the time the universe reached roughly 1 billion years of age, the process was completely finished. The vast fields of neutral hydrogen gas that had dominated the Dark Ages were permanently cleared away, leaving the intergalactic medium in the highly transparent, ionized state we observe today. The cosmic dawn was fully realized, and the universe had successfully transitioned from a dark, foggy environment into an open, clear reality where light could travel across billions of light years to tell its story to future observers. The photons from Jade's GS Z14-0 were flying through the universe while this great clearing was taking place. In fact, they were part of the very energy driving the transformation. As those specific light waves left their home galaxy, they had to push through the remaining pockets of neutral gas, losing some of their shorter wavelengths to absorption along the way. This interaction left a permanent mark on the light, creating the distinct spectral barcode that allowed modern astronomers to calculate exactly how much neutral gas was still present in the universe during that ancient era. As the light continued its lonely journey forward through time, it watched the universe grow up. It passed by generations of galaxies that were steadily organizing themselves into grand spiral and elliptical shapes. It witnessed massive cosmic collisions where entire galaxies ran into each other, mixing their star populations and triggering massive new starburst events. It flew through an expanding vacuum that was growing emptier and colder with every passing millennium as the distance between major galactic clusters became steadily larger. By the time the photons had travelled roughly halfway across their long journey, the universe was about 9 billion years old. In a relatively quiet, ordinary corner of a localized spiral galaxy that would later be named the Milky Way, a massive cloud of enriched gas and dust began to collapse under its own gravity. This cloud was heavily seeded with carbon, silicon, iron, and oxygen left behind by earlier generations of dying stars. As the center of this cloud compressed to ignite a new yellow star, the remaining debris orbiting around it began to clump together, forming a series of rocky and gaseous planets. This ordinary event was the birth of our Sun and the solar system we call home. The ancient light from Jades GS Z14 Rho was already incredibly old by the time the Earth formed. It had been traveling through the void for 9 billion years before our planet even existed as a solid rock. While the Earth was a molten ball of lava, the light was moving forward. While the first oceans formed and basic single-celled life began to develop in deep hydrothermal vents, the light was continuing its silent path through space. It flew past the eras of complex marine life, past the rise and fall of ancient forests, and past the millions of years when massive dinosaurs dominated the terrestrial landscape. When a massive asteroid struck the planet 66 million years ago, ending the age of the dinosaurs and allowing tiny mammals to inherit the Earth, the photons from JD's GS Z490 were already in the final stretch of their journey. They were entering the local neighborhood of the universe, closing in on the Milky Way. During the brief millions of years that followed, early human ancestors evolved, learned to walk upright, discovered how to control fire, and began building the very first civilizations on the surface of the planet. Think about how incredibly compressed human history is compared to the timeline of that single light signal. The entire story of human progress, from writing on clay tablets to building international combustion engines, happened while that ancient light was covering the final microscopic fraction of its journey. While humans were fighting local wars, building cities, and developing mathematics, those photons were silently crossing the remaining empty space between the galaxies, completely unaware of the tiny, conscious creatures waiting to intercept them. In the final few decades of this long journey, human beings developed the technological capability to leave their atmosphere and look out into the deep cosmos with specialized instruments. We built the Hubble telescope, discovered the accelerated expansion of space, and realized that our universe held secrets far older than we had ever dreamed. Then we spent 30 years designing, building, and testing a highly advanced golden eye specifically tuned to capture infrared light. We launched it into space, sent it 1 million miles away to L2, and carefully aligned its mirror segments. Just as the James Webb Space Telescope finished its initialization sequence and pointed its instruments toward the deepest dark, the photons from Jade's GS Z14 finally arrived, landing perfectly on the ultra-cold sensors after an uninterrupted journey of 13.5 billion years. To fully grasp the magnitude of this discovery, we have to look directly at the specific mechanics of how the James Webb Space Telescope processes this ancient light. When those precious photons from JD's GS Z14 Rho hit the large gold-coated primary mirror segments, they are not just taking a standard photograph. The mirror segments concentrate the faint infrared energy and bounce it cleanly toward the secondary mirror, which then directs the light down into the heart of the telescope's instrument module. It is here that an incredibly sophisticated device known as near-spec, the near-infrared spectrograph, begins its highly detailed work. NIR-spec is an absolute triumph of human engineering, designed to accomplish something that sounds completely impossible at first glance. It can observe up to 100 distinct cosmic objects simultaneously within a tiny patch of the night sky. To achieve this remarkable feat, engineers had to develop a brand new technology called a microshutter array. Imagine a tiny grid containing roughly 250,000 individual microscopic windows, each one measuring only a fraction of the width of a human hair. Every single one of these microscopic doors can be opened or closed independently using a computerized magnetic control system. By opening only the specific microshutters that line up perfectly with a faint target galaxy like Jades GS Z490, astronomers can completely block out the unwanted glare from brighter nearby stars and foreground objects. This isolates the ancient light signal perfectly, allowing it to pass cleanly through the instrument's internal optics without any outside contamination. Once isolated, The light is directed through a specialized diffraction, grating, or prism that splits the infrared beam into its individual component wavelengths. This creates a highly detailed, stretched out spectrum that reveals the hidden barcode of the distant galaxy. When scientists analyzed this infrared spectrum for jades GS-Z140, they were looking specifically for a physical feature known as the Lyman break. This break is an incredibly clean, sharp drop-off in the galaxy's light profile that occurs at a specific ultraviolet wavelength. It happens because the vast clouds of neutral hydrogen gas surrounding a young galaxy act as an incredibly efficient filter, completely absorbing any photons that possess wavelengths shorter than 91.2 nanometers. Consequently, the galaxy's light spectrum drops completely to zero at that precise point, creating a distinctive cliff-like feature in the data. Because the universe has been expanding continuously since that light was emitted, this distinctive cliff has been shifted significantly toward the red and infrared ends of the spectrum. By measuring exactly how far this cliff has moved from its native ultraviolet position, cosmologists can calculate the object's precise redshift value with absolute mathematical certainty. For JADES GS-Z140, the cliff was located deep in the infrared spectrum, confirming a record-breaking redshift value of 14.32. This empirical measurement means we are seeing the galaxy as it existed a mere 290 million years after the Big Bang, providing an authentic look into the deep past that completely rewrites our understanding of cosmic timing. But the details hidden within that barcode revealed an even greater scientific surprise. When researchers looked closely at the longer wavelengths within the infrared spectrum, they detected a clear, unmistakable bump in the emission data. This bump matches the highly specific energy signature of ionized oxygen gas. The presence of oxygen inside a galaxy this close to the beginning of time is a profound discovery that fundamentally shifts our perspective on the early universe. It means that the pristine, simple environment established by the Big Bang had already undergone massive chemical changes. To understand why this oxygen signature is so world-shaking, we have to revisit the basic periodic table of elements. The primordial universe contained only the three simplest elements: hydrogen, helium, and tiny traces of lithium. Every heavier element in the cosmos, including the oxygen we breathe, the carbon in our cells, and the iron in our blood, had to be forged inside the nuclear fusion furnaces of stars. There was absolutely no oxygen present when the first stars began to form in the darkness. For a notable amount of oxygen to be present inside JADES GS-Z140 by the 290 million year mark, an entire hidden history of stellar life and death must have already occurred. A previous generation of massive, short-lived stars must have ignited inside the dark ages, fused hydrogen and helium into oxygen deep within their intense cores, and then exploded as brilliant hypernovae to scatter those heavy elements across space. Only after this chemical enrichment took place could the gas clouds collapse again to form the star populations we are observing inside JADES GS-Z110. This single chemical signature provides empirical proof that this record-breaking galaxy was not a primitive pioneer. It was already a highly sophisticated, multi-generational stellar city sitting on top of a deep historical foundation. It means that even further back in time, during the earliest epochs of the cosmic dark ages, the universe was already working at an incredible pace, processing matter and building chemical complexity significantly faster than any of our computer models ever predicted. Whenever the universe behaves differently than our theoretical expectations, science enters its most exciting phase. The discovery of JADES GS-Z110 does not mean our basic understanding of the Big Bang is wrong, as some sensational headlines like to claim. Instead, it tells us that our specific models regarding how quickly gas can cool, condense, and organize into stars in the high-density environment of the early cosmos require major updates. Nature is demonstrating that it is far more creative, efficient, and industrious at building complex structures than humans had given it credit for. There is something deeply comforting about this realization. It reminds us that the universe still holds vast oceans of unknown truths waiting to be discovered. Just when we think we have mapped out the grand timeline of cosmic evolution and solved the major puzzles of the past, a tiny, faint smudge of infrared light, captured by a telescope orbiting 1 million miles away, can completely upend our assumptions. It forces us to remain humble, curious, and deeply appreciative of the slow, quiet messages that have been traveling through the darkness for billions of years just to tell us where we came from. The discovery of jades GS Z14-0 did far more than simply break previous cosmic records. It raised incredibly difficult, profound questions for the scientific community. According to a vast majority of our earlier theoretical models, a galaxy that is this incredibly bright, highly developed, and structurally stable should not have existed so incredibly soon after the Big Bang occurred. The young universe may have formed organized structures at a much faster pace than scientists had ever predicted in their computer simulations. Whenever the universe behaves differently than we expected it to, astronomy becomes especially interesting and exciting. Scientists certainly love being correct about their theories, of course, but discoveries become truly thrilling when nature quietly looks at us and says, actually, reality is a little bit stranger than you originally thought. That strange and wonderful possibility is a major part of what makes the James Webb Space Telescope's discoveries feel so vastly important to humanity. We are not merely filling in tiny details of an already completed map. Instead, we are entering completely unmapped territory where our core understanding of cosmic physics itself may need serious adjustment. Perhaps that is entirely fitting for our species. After all, every single generation throughout history thinks it understands the cosmos fairly well, right before the universe casually pulls back a curtain to reveal something absolutely enormous, hiding in the deep darkness. In the centuries ahead, humans may discover distant galaxies that are even older than JD's GS Z14-0. The James Webb Telescope itself may continue to uncover even more ancient structures that are waiting quietly at the absolute edge of visibility. Perhaps someday, another generation of highly advanced telescopes will look even farther back toward the mysterious era of the very first stars themselves. They will look toward the exact moment when the cosmic darkness first began breaking apart under the brilliant glare of newborn light. Try to imagine a universe completely without stars for a moment. Not a cloudy night sky, where the familiar stars are simply hidden behind weather systems on Earth. Not a bright city sky washed pale by rows of streetlights and glowing office windows. Imagine a universe that is genuinely, completely without stars anywhere in existence, no galaxies hanging in the far distance, no planets orbiting in the dark, no constellations to map out, and no familiar points of reassuring light at all. Only a pure, total darkness gradually unfolding across the vastness of expanding space. It feels incredibly strange and deeply unnatural to us because our human brains are highly tuned to looking for structure and order. Humans naturally organize the chaotic night sky into predictable, neat patterns. We connect distant stars together to form shapes of celestial hunters, massive bears, and grand mythological creatures carrying heavy swords, for reasons that absolutely nobody fully questions anymore in modern times. We give unique names to galaxies. We place labels on vibrant nebulae. We divide the infinite cosmos into neatly understandable pieces, because our species is deeply uncomfortable with an enormous, unnamed emptiness. But there was an incredibly long period of history before any of that organization existed. Long before galaxies had designated human names, long before galaxies had recognizable structural shapes, and long before galaxies properly possessed any unique identities at all, the universe was still trying to become a place where such things were even physically possible. Oddly enough, this grand story starts with conditions so incredibly extreme that almost every single normal human comparison completely fails to capture the reality. When the first stars finally did begin to appear, they completely transformed the environment around them. Their high-energy radiation began to ionize the surrounding neutral gas, gradually transforming the vast landscape of intergalactic space. The universe became transparent again, over increasingly large scales, clearing the cosmic fog. But exactly how and when this magnificent clearing occurred remains one of cosmology's greatest, most intensely debated questions. Galaxies like Jades, GS, Z40 provide invaluable clues to researchers because they existed directly during this highly transformative era of cosmic history. If bright, massive galaxies already populated the universe by redshift 14, they may have contributed substantially to the ionization process itself. In other words, these early galaxies were not merely passive, quiet objects forming inside a static cosmos. They were actively reshaping the entire universe around them with their energy. Tiny, concentrated regions of intense star formation were directly influencing the fundamental physical state of intergalactic space across absolutely enormous distances. Perhaps that revelation tells us something much deeper about cosmic evolution as a whole. Generally speaking, absolutely nothing in the universe evolves completely independently or in total isolation. Galaxies heavily influence the surrounding intergalactic gas clouds. Radiation from early stars directly affects how future star formation can take place. Massive supernova explosions permanently alter the local chemistry of space. Supermassive black holes actively regulate galactic growth over time. The universe develops through highly interconnected feedback processes that are constantly interacting across vast, mind-boggling scales. Everything in existence affects everything else. Furthermore, JD's GS Z140 reveals something utterly fascinating about the concept of cosmic timing. Human intuition naturally tends to severely underestimate how quickly nature can organize raw matter under the steady, unyielding influence of gravity. Given billions of years of time, absolutely anyone would expect to see complex galaxies eventually form. But the James Webb Telescope strongly suggests that galaxies emerge very early indeed. The first large cosmic structures may have successfully assembled astonishingly soon after the Big Bang occurred. Perhaps this realization should not surprise us completely if we look at the math. Gravity is a cumulative force. Tiny density fluctuations left over from the birth of the cosmos grow steadily larger over time. Regions containing even slightly more matter naturally attract additional matter, strengthening and accelerating the process continuously. Once the initial gravitational collapse begins, structure formation can speed up rapidly. This is especially true in a much denser, younger universe, where early galaxies existed significantly closer together and physical interactions occurred frequently. The cosmos may naturally favor rapid, efficient organization under those early high-density conditions. That realization fundamentally changes how modern astronomers think about the transition from absolute simplicity to complex structure. The universe may not require long, quiet, dormant ages before its cosmic creativity begins. Complexity appears remarkably quickly. The very microsecond physical conditions allow it to happen. Another massive implication of this discovery concerns chemical evolution. The earliest universe contained mostly simple hydrogen and helium gas. All heavy elements formed much later through intense stellar fusion and dramatic supernova explosions. This means that galaxies like Jades GS Z140 existed during one of the very first major phases of chemical enrichment in cosmic history. Deep inside those early stellar furnaces, the universe was actively manufacturing the essential ingredients required for future rocky planets and complex biology. Carbon, oxygen, silicon, and iron are the fundamental building blocks of rocky worlds and living systems. The James Webb observations help astronomers investigate exactly how quickly this critical chemical evolution began, and the answer again appears to be surprisingly fast. The young universe may have become chemically complex far earlier than any expert expected. One early generation of stars formed and died with incredible speed. Heavy elements spread outward into the surrounding gas clouds. Future generations of stars immediately inherited these chemically enriched environments. The cosmos evolved chemically through powerful feedback loops operating across astonishingly short cosmological timescales. Eventually, billions of years later down the line, those exact same processes produced planets like Earth. This means that ancient galaxies like Jades, GS, Zidao 4 Nuolamuro belong not only to a distant, detached cosmic history, they belong directly to the absolute beginning of our very own material story. Before the deployment of the James Webb Space Telescope, humanity could easily create elaborate mathematical theories about the cosmic dawn, but we severely lacked detailed, direct physical evidence to back those calculations up. The earliest galaxies in existence remained partly or completely hidden away behind frustrating technological limits that our ground and space instruments simply could not overcome. Then quite suddenly and dramatically, a brand new mechanical eye opened up much deeper infrared windows directly into the highly energetic young universe, and the cosmos instantly revealed something completely unexpected to the teams of scientists waiting below. This exact developmental pattern has appeared repeatedly and predictably throughout the grand history of science. Whenever our species invents new physical instruments, those instruments fundamentally change reality. Now, to be perfectly clear, they do not change objective reality itself, but they completely alter humanity's accessible version of what reality is. When Galileo pointed his primitive glass telescopes directly toward the bright disk of Jupiter centuries ago, he was shocked to discover multiple hidden moons orbiting another planetary world entirely. Later on, Edwin Hubble used massive mirrors to reveal that our universe was populated by vast numbers of expanding galaxies. Eventually, the birth of radio astronomy uncovered completely invisible cosmic structures that have been silently radiating energy all around us for billions of years without anyone ever knowing. Now, the James Webb Space Telescope is exposing the universe's earliest galaxies with absolutely astonishing structural detail. Advanced technology completely changes our perspective. That new perspective systematically alters our scientific theories, and those theories ultimately transform our entire understanding of the universe. This evolutionary process of discovery never really ends. One subtle but profoundly beautiful implication of Webb's newest discoveries involves the definitive universality of physical law across all of time and space. Think very deeply about what a galaxy like Jades GS Z4 0 actually demonstrates to us when we analyze its data. Infrared light that was originally emitted over 13.5 billion years ago behaves according to the exact same fundamental physical principles we observe inside our modern laboratories today. Gravity worked precisely the same way back then. Nuclear fusion operated with the same rules. Electromagnetism behaved identically, and microscopic atomic physics functioned perfectly. The exact same natural laws governing the stars and galaxies around us right now were also governing them near the very absolute dawn of cosmic history. This absolute consistency across billions of years of deep time and completely unimaginable physical distances remains one of the most truly astonishing facts in all of modern science. The vast universe is ultimately comprehensible to us precisely because physical law appears to be completely stable and unchanging. Without that underlying material stability, astronomy itself would instantly collapse into complete chaos. Instead, ancient photons fleeing from distant galaxies carry highly structured, understandable, historical information directly across cosmic time, and humanity has developed the capability to successfully decode it. Furthermore, there is another absolutely fascinating consequence of all this information. Distant galaxies, like Jades GS Z14 suggest that mature-looking cosmic structure may emerge completely naturally and repeatedly throughout the universe whenever suitable material conditions are met. The cosmos seems remarkably, almost chillingly good at building complex galaxies. It does not do so hesitantly or eventually after endless eras of waiting, but rather quickly, perhaps even inevitably. Given basic matter, the steady pull of gravity, and a little bit of time, the universe appears heavily biased toward producing highly organized structure. This realization should completely transform how we view the early history of the cosmos. The young universe did not suddenly invent fully mature, perfectly shaped spiral galaxies overnight, like the ones we see in our immediate cosmic neighborhood. Those early systems were actually incredibly chaotic, messy collections of churning gas, dense dark matter, intense radiation, and rapidly forming populations of massive stars. They were the raw, violent, messy construction zones of the cosmos. And somewhere deep among those highly primitive, turbulent structures lies the true, unfiltered beginning of galactic history itself. Modern astronomers are constantly trying to locate that definitive beginning. One especially exciting possibility that researchers discuss with immense enthusiasm involves the strategic use of gravitational lensing. As Einstein famously predicted, gravity bends the path of light itself. Extremely massive cosmic objects, such as giant clusters of galaxies, can distort the fabric of space-time strongly enough to act as giant magnifying glasses for much more distant galaxies positioned directly behind them. In essence, nature creates its own incredibly powerful telescopes out of space itself. This spectacular natural magnification allows astronomers to observe ultra-faint objects that would otherwise remain completely invisible to our human instruments. The James Webb Telescope already uses gravitational lensing in several of its major deep-field observations to peer even deeper into the ancient universe. It is highly likely that future surveys using these cosmic lenses strategically will eventually uncover galaxies that are even older and more distant than Jades GS Z14-0. We will see tiny ancient systems clearly amplified by the specific geometry of the universe itself. There is something deeply elegant about the idea of the universe actively helping humanity observe its own grand beginnings. Yet, despite all of this immense excitement, modern astronomers always remain deeply cautious, and for very good reasons. Extreme redshift measurements are incredibly difficult to confirm with absolute certainty. A single rogue data point or an unexpected instrumental anomaly can easily lead researchers down the wrong path. That is precisely why the rigorous process of spectroscopy is so vital. By carefully breaking light down into its individual component wavelengths, scientists can confirm these incredible ages with absolute mathematical precision. This systematic approach ensures that our maps of the early universe are built upon solid empirical foundations. Every single confirmed data point brings us one step closer to understanding the true origins of cosmic complexity. When we reflect deeply on the sheer journey of these photons, the scale of the cosmos becomes almost overwhelming. The light captured from Jades GS Z4-Waro travelled uninterrupted through an expanding void for over 13 billion years. It escaped from a highly dense, chaotic environment when the universe was only a fraction of its current age. It sailed quietly through the cosmic dark ages, witnessed the birth of the very first stars, and drifted past generations of evolving galaxies. As that light travelled patiently across the expanding void, our own solar system had not even begun to form out of its pristine nebula. The gas and dust that would eventually coalesce into the Earth, the oceans, and every living thing were still scattered widely across interstellar space. The photons outlasted the entire life cycles of countless stars and outlived the rise and fall of unknown celestial structures. They crossed an unimaginable expanse of space that was continuously stretching and growing around them. Then, after this unfathomable journey across space and time, those exact same photons finally struck the gilded mirrors of a human-made instrument orbiting perfectly in the deep freeze of space. A species that had only recently learned to build campfires and track animals across earthen plains had successfully built a tool capable of intercepting messages from the dawn of time itself. This profound connection between the microscale of human history and the macroscale of cosmic evolution reveals the true power of scientific curiosity. We are a tiny part of the universe that has finally figured out how to look back and understand the whole. To fully understand the grand legacy of this record-holding galaxy, we must appreciate the deep philosophical quiet that comes from studying the edge of the observable universe. When astronomers sit in their quiet offices late at night, staring at the faint infrared signatures of jades GS Z14-0 on their computer monitors. They are looking directly at a monument to cosmic beginnings. This tiny, unassuming smudge of light represents a profound bridge across deep time, connecting the highly sophisticated technology of modern human beings with the raw, chaotic forces that shape the early cosmos. It reminds us that our small planet is not a detached island floating in a separate vacuum, but a direct consequence of a continuous material story that began billions of years ago. The physical parameters of JD's GS Z4-0 continue to challenge our standard theories of how structure grows. For many decades, textbook models suggested that early matter required long, drawn-out eras to coordinate into large stellar systems. Yet the definitive spectroscopic data gathered by the James Webb Space Telescope demonstrates that the early universe possessed a remarkable, almost terrifying efficiency when it came to assembling massive galactic structures. The cosmos was actively building complex star-filled cities containing hundreds of millions of solar masses in a tiny fraction of the time that previous scientific consensus deemed possible. This hyper-accelerated timeline forces us to look much more deeply at the localized physics of the infant universe. Because the entirety of space was significantly smaller and tighter, during those early epochs, the density of gas was incredibly high. This dense packing meant that gravitational collapse could proceed with immense velocity. Pockets of neutral hydrogen and helium gas did not merely drift hesitantly. They collapsed downward into deep dark matter wells with relentless force, triggering powerful starburst events that lit up the ancient darkness simultaneously across vast dimensions. The discovery also highlights the critical importance of chemical evolution in defining the eras of the cosmos. The discovery of a strong oxygen signature inside a system at redshift 14 demonstrates that the early universe was rapidly shedding its primitive chemical simplicity. Entire generations of massive, short-lived population 3 stars had already completed their dramatic life cycles, manufacturing heavy elements deep within their nuclear furnaces and scattering them across space via massive hypernova detonations. This chemical enrichment altered the physical properties of the interstellar gas forever, allowing it to cool much more efficiently and setting the stage for the creation of smaller, stable, long-lived stars like our own Sun. This means that systems like JD's GS Z14-0 are not strange, isolated anomalies. They are genuine ancestral structures, representing the foundational stepping stones that made our modern, complex universe possible. Without the rapid, highly efficient work of those early galactic factories, the cosmos would have remained a cold, chemically stagnant desert, devoid of the heavy elements necessary to build rocky worlds, solid land, wide oceans, or biological organisms. Every single atom of carbon in our DNA, every breath of oxygen entering our lungs, and every trace of iron circulating in our blood can be traced directly back to the intense nuclear processing that was already occurring inside those ancient hyperactive stellar cities at the absolute dawn of history. As the James Webb Space Telescope continues its silent orbit around the second Lagrange point, a million miles away from Earth, its golden mirrors remain trained on the deepest darkness of the sky. It operates in an environment of extreme freeze, completely shielded from the disruptive heat and light of our home planet. From this pristine vantage point, it continues to gather faint, ancient photons that have been traveling through the vacuum for over 13 billion years. Each new dataset it beams back down to Earth has the potential to push the boundaries of human knowledge even further back into the Dark Ages, closer to the mysterious moment when the very first lights switched on in the cosmos. This ongoing endeavor demonstrates that human curiosity is a truly extraordinary force. We are physically confined to a tiny, fragile, rocky world, orbiting an ordinary star in a quiet corner of a single galaxy. Our lives are brief, lasting for only a microscopic flash on the grand scale of the cosmic calendar. Yet, by using our minds, our mathematics, and our sophisticated instruments, we can transcend these physical boundaries entirely. We can reach across billions of light years of empty space and reconstruct the deepest history of the cosmos. reading the ancient light signatures of a universe that was busy becoming itself long before our planet was even a remote possibility. The story of jades GS Z14-0 is ultimately a testament to the power of observation and patience. The universe does not reveal its deep structural secrets easily. It requires humanity to look with immense precision, to build complex tools, to risk decades of engineering effort, and to listen carefully to the faintest whispers of heat arriving from the edge of time. And when we do look with that level of devotion, we discover a reality that is far more active, creative, and beautifully complex than we ever dared to imagine. The ancient cosmic dawn was not a slow, hesitant awakening. It was a brilliant, rapid explosion of structure and light that set the permanent architecture of reality in motion, leaving behind a historical record that we are only just beginning to truly decode.